Yeah, let's get a little more participation up there. I only see Cody, Timothy, Noah, Seraphim. So looks like we're doing pretty well with what we're remembering from yesterday. All right, so thinking about the different types of waves, right? So a longitudinal wave, the memory trick we have is thinking about how the particles move along with the energy. So that would be the top option right here with the spring, how the coils of the spring are contracting along the same path where the energy is moving, kind of like the particles. And then a surface wave is the one where the particles on the surface are traveling in bigger circles than the particles like that are beneath the wave. We don't have that exact diagram right here, but all you need to remember about the surface wave is that kind of like how they move in that circular motion. Then with the transverse wave, the particles are moving perpendicular or up and down to the direction of the wave. All right, guys, so great job on that. Let's go over some announcements. Please don't share any personal information during class, guys. And we are looking for your participation as always, and that these sessions are still being recorded for learning purposes. All right, let's move on. Today is Tuesday. We only got 20 days left in the semester, so we're quickly approaching the end. In terms of our lessons, today we're learning about sound. So yesterday we introduced waves. Today is going to be specifically about sound waves. And we're going to, with that, we're going to define frequency and determine the frequency from a graph. We're going to measure it. And then we're going to define the properties of a sound wave and understand how sound moves through different mediums. All right, let's go ahead and get our notes open. All right, we do have links toward the bottom of the chat. Again, if neither of them work, then you can always access your notes through your grades tab. All right, be sure to raise your hand.
All right, everyone. So this is a quick reminder in case you weren't here yesterday that I am going on maternity leave in 2 weeks from yesterday. So on May 24th, Monday, May 24th, and I will not be returning for the remainder of trimester 3. So that being said, to make sure that you are all caught up on all of your work, I will be having office hours. I'm doing well, thanks, Lexi. I will be having office hours every single day for the next 2 weeks at 2 p.m. to help you with projects. Now, the reason for this is because I don't exactly know the substitute situation for when I leave. So it's imperative, really important, that you have your projects as caught up as possible before I leave. So remember, we have the Unit 1 airplane project, we have the Unit 2 drop project, and the Unit 3 roller coaster project. All right, so really recommend have those all squared away before I leave, just in case, because we don't exactly know, again, what's happening with subs. Just in case, you do want to make sure that those are as completed as possible. Awesome, Jonathan. That is great to hear. Additionally, for the same reason, since I'll be leaving, we will be replacing the Unit 4 project with the Unit 4 exam, just to make grading a little bit easier for our substitute teachers if we end up with subs or whatever is going on with that. Final exam is still the final exam, so that has not changed. But again, these 3 projects, really important. Again, they make up over 70% of your grade, so if you want to pass the class, you do need to make sure that you do those projects well. Again, they're graded on a 5 through 10 scale, so we actually grade very generously for them as long as you try on every slide and it's obvious that you watch the recording while doing the project, right? So if it's clear you watch the recording, it's graded on a 5 through 10 scale. The lowest grade you could get on it is a 50%. So make sure you're getting those submitted. Very important. All right, so let's go ahead and do a quick brainstorm. So remember that sound is what we call a mechanical wave. We took a look at some examples of mechanical waves during our brain stretch today. So mechanical waves, remember, they do require a physical substance, a medium such as a gas, a liquid, or a solid in order to move. So what's happening in sound is one air particle is going to vibrate, hit the next air particle, and so on and so forth, like a giant game of telephone, but with sound particles. All right. Now, these particles do move parallel to the energy or along with the energy. So sound, tell me in the chat, is that a transverse, longitudinal, or surface wave? Tell me in the chat. Again, we just reviewed these: transverse, longitudinal, and surface, all right? So if it's moving parallel or along with the energy, tell me what type of wave is that? Hint, hint, it's moving along with the energy. Tell me in the chat. Excellent, I see Shayna in the chat. Cody. Well, remember, if it's moving parallel back and forth along with the energy, the long part should remind you of what that is. All right, that's the hint to remember if it's transverse, longitudinal, or surface. Excellent. I see Lexi in the chat. I see Mallory. Yeah, exactly. This is longitudinal, right? So longitudinal. We can actually see longitudinal. We can actually see that word long in it. So the particles move along in the same parallel direction as the sound, right? So again, if our energy is moving left to right, our little particles shake back and forward, left and right, okay? So again, this is energy, and this is the parallel particles. Again, they're still kind of staying in their seat. We talked about that yesterday. They never leave their seat, but they are moving back and forth in the similar direction. Oh, yes. Yeah, maternity leave means I'm having a baby, in case anyone doesn't know that. That is what's happening. I forgot to clarify that for a previous class, too. And they were like, what? What does that mean? All right, so the question then is, tell me in the chat, can sound travel in outer space? All right, tell me in the chat, is there a medium, a physical substance in outer space for sound to travel through? No. Okay, so remember that this space right here is all empty space, right? So what we call a vacuum, an empty vacuum of space, and there's nothing there to carry the sound. Sound needs particles. If there are no particles here, there's no air, there's no water, there's no solid, there's no steel, earth, etc., then sound cannot travel. All right, so anytime you've ever watched a movie or a TV show where you see a huge explosion in outer space and you hear the explosion from outside the ship, that is not what happens. That is not true. You would not hear anything from that explosion. All right. Now you might hear something from inside the explosion, all right, because there is air inside of the actual ship, but not on the outside. Awesome. So again, this is a longitudinal wave. Sound is always longitudinal. And again, we can hear it if we're inside the ship where there is particles, but we cannot hear it from the outside where there are no particles to carry that sound. Smiley faces, emojis in the chat if that makes sense. Again, kind of differentiating between our mechanical, physical waves versus our electromagnetic or light waves. Beautiful. I see lots of smiley faces. All right, so let's go ahead and talk a little bit about frequency. So frequency is a new vocab word. It's going to be the number of overall cycles that occur in 1 second. Okay, so we measure this in cycles per second, or another unit that we can use is hertz, H-E-R-T-S, H-E-R-T-Z, the abbreviation for that being capital H, little z. Okay, so frequency we're going to learn is going to be important when we also talk about period later on. So frequency and period have to do with how sounds sound. All right, so frequency has to do with how high or how low a sound actually sounds to our ears. But let's go ahead and talk about how we actually solve for frequency. So when you look at a graph of a wave, the way that you can solve for frequency is by looking at the number of cycles in 1 second. So you can see I have 1 second of the wave here, okay, and I need to find the number of waves that are occurring here, okay? Now remember that a single wave can be measured by either going from one identical point to another identical point. So you could go from crest to crest, the tops, or trough to trough, the bottoms, or you can go from two identical equilibrium points, which is what we're doing here. So you can see I'm going from where we cross above the equilibrium to again where we cross going up across the equilibrium. Okay, so here's the deal. Each wave cycle, just so you know, when you measure from equilibrium points, each wave cycle has to have 2 bumps, a top bump and a bottom bump. Right, so you can see here this is one wave cycle with a top bump and a bottom bump. Okay, so go ahead and point for me on the board, where would the next wave cycle end? Okay, so here's our first one. Go ahead and point for me on the board with your colored pointer. Where does the next one end? Find a top bump and a bottom bump. Go to the end of the top bump and the bottom bump of the next one. Now, right now we're pointing at for only a top bump. I need a second bump, top and bottom. So go to the next one. There we go. I see greens on it. Pink, purple, move over. There we go. Yes, that would be our next wave cycle. All right. So right here, this is actually our next wave cycle. Again, we have a top bump and a bottom bump. And finally, where's our next one? Where's our next one? Go to the next one. Again, follow that until we've had both a top bump and a bottom bump, an identical wave cycle. Thank you, thank you. Purples, move on over. There we go, beautiful. So yes, this would be our next wave cycle. So in total, right, I've got one wave cycle here. Tell me in the chat, how many do you see in total? So we've got one wave cycle here, two wave cycles here. How many do you see in total? We're saying 4, but take a look at how I labeled this. This is the first one. This is the second one. So this should be the third one. Yes, so we have 3 cycles here. And so in 1 second, if I have 3 cycles, that means my frequency is 3 hertz. Go ahead, give me a green check, orange X if that's beginning to make sense. Again, I know it's kind of a lot of information at once, so just tell me if it's starting to make sense, and we will continue to practice. You will have one that you'll need to apply on your own. Beautiful. All right, let's go ahead and keep on moving here. Oh, oops, sorry. This is our answer to number 2. Go ahead and raise your hands for number 2. The first box should be 3. And the second box should be HZ for hertz. Awesome, Jonathan. All right, I'm going to go ahead and give you 20 seconds. Raise your hands for number 2. Okay, so let's now go ahead and take a look at this next problem. So again, frequency is the number of overall cycles in 1 second. So we need to find the number of cycles in 1 second here. You can see I have a 1 second clip here. And then we'll label that with hertz, our units here being hertz. So taking a look here, we need to go ahead and first mark off the number of cycles that we can see. So taking a look here, you should be able to see that here's our first cycle that we indicated. All right, and then moving along, we're going to go ahead and follow this and see a top bump and a bottom bump. So my second cycle ends here. All right, so this is my second cycle right here. And then continue to move along, right? I have a top bump, a bottom bump. Here's my third. Top bump, bottom. Here's my fourth. Top bump, bottom, fifth. Top bump, bottom, sixth. All right, so here we go again. Taking a look here, don't count the actual dots. Remember to count the actual overall waves. So right here's our third wave, our fourth wave, our fifth wave, and finally our sixth wave. So if we have 6 waves in one second, right, 6 cycles in 1 second per 1 second, that is going to give us a final answer here of 6 hertz. Right, so our frequency here should be 6 hertz. Make sure you understand that because you will need to do the next one on your own. All right, so again, your answer for number 3 is that this is 6 hertz. You can see the 6 different cycles that we had here. Go ahead, take 20 seconds and mark that in your notes for number 3. All right, everyone, so let's go ahead and take a look at this last one. So again, we need to find the number of overall cycles here. So go ahead and point for me up on the board, right? I already showed you the first cycle here. All right, go ahead and show me up on the board. Where does the next cycle end? Where does the next cycle end? Again, we need to find a top bump and a bottom bump. That's just the top bump. Keep on going. We need the top and the bottom bump. Keep on going. Keep on going. Where does the next cycle end? There we go. Pink is on top of it. I see red. There we go. There's the end of our next cycle, right? So this right here would be our second cycle. All right, go ahead and show me where should I put my next dot. Don't put answers in the chat. This is a complete on your own. Don't put answers in the chat. Yep, there's our next cycle. Where's our next one after that? Keep on going, keep on going. Again, find a top and a bottom bump. Yep, there it is. And where's our last cycle? Keep on going. Perfect, perfect. Yep, there's our top and our bottom bump. No worries, Jonathan. So again, you need to count up the total number of overall waves that you see. Don't count the dots. Again, kind of put the number in between the dots. This is going to be our answer to number 4. Go ahead and work on this. First box is going to be your number. Second box will be HZ for hertz, right? So first box is the number. Second box Second box should be capital H, lowercase z, just like we practiced that. All right, if you need to check your answer, we're in the Q&A area. Otherwise, go ahead and raise your hands when you are ready to move on. You have 30 seconds. Go, go, go. Okay, so let's go ahead and talk about how we can actually graph sound. So sound waves, we said, are longitudinal, right? That means their particles are moving back and forth along with the energy. So this is a lot of what sound looks like, right? A bunch of particles kind of being squished together, passing along the message of your sound wave. So those particles, again, kind of move parallel to the energy. However, when you actually graph the pressure that's occurring in a sound wave, it does end up looking very similar to a transverse wave. So mathematically, it looks a lot like a transverse wave that goes up and down. However, it's not physically a transverse wave. Smiley faces, emojis in the chat if that makes sense. All right, so mathematically, when you graph it, it looks like a transverse wave, but again, physically, it's actually longitudinal. Cool. All right, so we learned about these vocab words the other day where we talked about a crest. So remember, a crest is the highest point. So the graph's crest, or the highest point of our graph right here, okay, which I'll do in a different color, right here, okay, that is a crest. That corresponds to graphing high pressure, okay? Oh, no worries, Lena. I'm sorry that happened. Yeah, maybe New Row's having issues. Now, an area of high pressure in the physical wave, just so you know, is called a compression. All right, so on the physical wave, high pressure is called a compression. On the graph, the high point is called the crest. So again, that's important to understand. The crest and the trough are what we're talking about on the graphs. The compression and what we'll learn about rarefaction, that's what we talk about physically, okay? So the trough, on the other hand, again, the lowest point on a graph, is going to correspond with the lowest pressure. And the lowest pressure areas physically of a sound wave are called rarefactions. So let me go ahead and write that in, rarefactions, okay? So again, compression, rarefaction, that's the actual compression, rarefaction. That is the actual pressure on the real sound wave. Whereas when we talk about crest or trough, that's those points on the graph. Okay, so that's important to understand the difference between those. All right, let's go ahead and talk a little bit about actually seeing these. So just how many of you have ever used a tuning fork or seen a tuning fork? It looks like this. It's used oftentimes with like instruments, or if you've ever been done singing before. Yes or no, let me know if you've ever seen a tuning fork. If not, I have a video that's going to show you a tuning fork in just a moment. So yes or no in the chat, have we seen a tuning fork before? Cool, all right, so Lena, you have, Itati, you haven't. Okay, well, no worries, we're going to see one in just a moment. Tuning forks are really cool though because they vibrate at specific frequencies. And remember, I mentioned that we're going to be learning about this more later, but frequencies are related to the type of sound that you hear. So high frequencies sound very high-pitched. Low frequencies sound very low pitched. Okay, so we just learned about frequency. So tuning forks vibrate at specific frequencies or specific notes, and what they do is they push the air particles around them, right? So when they're close together, when they push the particles close together, they're creating high pressure or compressions. When they're very widely separated or low pressure, remember those are going to be rarefactions. Okay, so you can see that right here, again, close together, compression. Further apart, you can see the rarefactions. Okay. Now, a tuning fork vibrates very fast to push that air to make that frequency. All right. And it can be hard to visualize that because we can't actually see the air. However, you can actually see a tuning fork in action, and we're going to go ahead and show that to you in a video. So let me go ahead and drop this up on the whiteboard for us. And you need to go ahead and be ready to give me observations about what you see. So let me first share this up on the board, and then I'm going to go ahead and actually get the video. So give me one moment to grab that video. This is from the slow-mo guys. If you don't watch the slow-mo guys, you definitely should because they're a lot of fun. All right, here we go. Be ready to give observations.
A. Sounds like A.
Sounds like A, definitely. A, yeah.
So I've heard that a tuning fork, when you dunk it in water, the frequency vibrates the water in a cool way that looks good in slow-mo.
Yeah, it tickles.
Yeah?
Yeah.
Oh, yeah. So I have some choices for you, Dan. Do you think it will look A, really crap and not good, B, rubbish, or D, really awesome?
Really awesome.
Right, let's do it. Alright, give it a right whack and
Give
then...
it a right whack. Ready?
Yeah.
Let's go.
Whoa.
Whoa.
You had some serious bloody splashback for that, didn't
Serious splashback. It's like the smallest little bit of splash in the world.
Oh.
Whoa.
That's severe.
Oh my god.
Might have been over exaggeration. Alright.
All right, so go ahead and tell me in the chat, what did you observe there? What did you observe happening? Again, it can be hard for us to see sound in real life because usually it's traveling through air, but what did you notice here? Go ahead and let me know in the chat, what did you observe? I need responses. There we go. Perfect. Thank you. I see Jonathan in the chat. Let's get some more participation. There we go. Thank you, Angelina. Let's get Kamal, Carlos in the chat, Matthew, Alan, Kalina, Chantel. What did you notice happening? Yeah, exactly. So we can see that when we put the tuning fork in, which emits sound, right, we can actually see that the water vibrated. So again, sound is just a vibration, right? So that's kind of a visual of how sound is a vibration. Smiley faces, emojis in the chat, if that makes sense to everyone. Again, sound is just a vibration. It's just a wave. It's just a wave. Cool, cool, cool. All right, let's go ahead and match these up. Please work quickly because we still have quite a bit to get through, and we're going to run out of time, so please work quickly.
Yeah, please work quickly. We've got compression. I believe you pronounce that refraction or raw refraction. And then crest and then trough. Let's go ahead and see that, yeah, you guys are doing pretty accurate work there. So yeah, for number 5, compression, the area of high pressure in a sound wave. The refraction is an area of low pressure in a sound wave. And then the trough is the lowest point on a graph. And then the crest is the highest point on a graph. So please raise your hands for number 5 as quickly as we can. We're going to do a little brainstorm here. All right, so in the chat, take a look at the speed of sound in the different mediums that we have here in the table and look at the speed of the sound compared to those mediums. So what do you notice about those different measurements? What is changing? So versus like the speed that the sound is traveling at. But with these mediums, yeah, steel is going to be the fastest, but generally, right, the sound is going to be traveling faster through solids. Then the next slower is going to be liquids, and then the slowest is going to be through gases. And that has to deal with how closely the particles are packed together. Notice how in a solid state, they're right next to each other. Liquid state, they're moving around each other, but still dense. And the gas is the least dense.
All right, so let's go ahead and watch this video here. Again, you need to be making observations. So we need to figure out which medium do you see sound kind of traveling the fastest. Again, this is kind of an analogy. So let me go ahead and pop this up on the board again. Again, I'll try to share the sound through my headphones instead of the actual screen share, just because that seems to be better for y'all. Let me go ahead and find this one.
Now sound is a disturbance. Now to prove this, what I've done is I've arranged these dominoes equidistant from each other, which I will call it as particles of the medium. And this here is a balloon which is going to act like the eardrum. Now I'm only going to disturb the first particle, and let us see if the disturbance reaches the eardrum. Now what you have seen is I disturb the particle, and each particle disturbs the next particle. Now the particles have not moved from their place. They are in the same place, but the energy has been transferred to the eardrum. So are you ready to sport? this is a race between solid, liquid and gaseous medium. Now see what I've done. This blue and purple dominoes, I place them close to each other, and this is going to be my solid medium, because in solid medium particles are closer to each other. Now coming to the red dominoes, this red dominoes, I place them at a slightly greater distance, and this is going to be the liquid medium. Now coming to the yellow dominoes, of course you have guessed by now, the yellow dominoes are going to be my gaseous medium, because here the particles are far away from each other. Now we are going to create a disturbance at the same time instant. Let us see who is the fastest. So let me begin the disturbance, and I'm going to start this particular disturbance at the same time instant. So now it is clear the disturbance travels fastest in the solid medium. So where will sound travel faster? Of course, the solid medium. So sound is fastest in the solid medium, slightly slower in the liquid medium, and much slower in the gaseous medium. So this was an experiment to show you that in solid, liquid and gases, sound travels fastest in the solid medium.
All right, everyone. Awesome. So let's go ahead and talk a little bit about what he observed, right? So tell me in the chat, where did sound travel the fastest? Where did sound travel the fastest? All right, I can go ahead and show you kind of a clip from here. Awesome. I see Jonathan in the chat. I see Kaden, Shayna. Yeah, in our solids. Again, he said that the reason why is because in the solids, the particles are much, much closer together. And so because they're much closer together, they're able to pass on that message of the energy of sound much quicker than, for example, the liquid right here, or the gas right here. So interestingly enough, you and I talk all the time in gas, right? We talk in air, but that's actually the slowest way to communicate, right? It's actually a lot faster to communicate, for example, underwater. So if you're ever underwater with a friend, you can yell at them and they'll hear you much faster underwater and over longer distances than they would in the air. Or with solids, like if you knock on wood and put your ear against the wood, or steel, the sound can travel very fast and over very long distances. Okay, so the speed of sound generally increases when molecules are closer together in a medium. Again, that's why sound travels faster in water. Whales in the ocean can actually communicate across huge distances because of how much faster sound can travel in water than in air. Over time in air, it just runs out of energy, and so you just can't communicate as far in the air. And again, we just saw that is definitely fastest in solids, right? Steel, for example, sound can travel 20 times faster than it can in air. Another small factor here is that sound actually travels faster on hot days than on cold days. And the reason is because on hot days, the air particles are actually moving a little bit faster than on cold days. So again, the faster you're moving, the closer those molecules are, the faster they can actually pass on that message, pass on the sound. This is number 6. Go ahead and fill in the blank with the word solids and only the word solids and raise your hands. It is plural, so don't forget that last S.
Sound waves, using our whiteboard tools, putting a box around the correct answer. All right. Keyword, what is not true about sound waves? This right here has cost me many, many points on many, many exams. So please be sure that we're reading that's not true. And say that, yeah, you guys are pretty much spot on. Yeah, so a sound wave is not an electromagnetic wave, right? It does involve light or magnetism. It involves mechanics, right? It's literally moving the air molecules back and forth along the motion of the energy as it travels to our eardrums. So go ahead, mark letter B for number 7. All right, one last timer here, one last raising of the hands, and then that will be it for today. Go ahead and end it then. You guys did amazing today. We learned about frequency and determined frequency from a graph by counting those high points and low points. We define the properties of a sound wave, and we understand how sound moves through different mediums. So let's go ahead and just say that if you haven't submitted your notes already, go ahead and submit them. Have a great day, guys, and we'll see you tomorrow.